Okay, let's take a look at problem 3 on the practice exam. So here you're given a PDF with an unknown parameter theta, and the problem in this problem we want to estimate this unknown parameter theta, and you're given some data. X has this population that's given. I'm sorry, the PDF that's given, and then so we've collected samples of X, and we've got the 10 samples listed. Now notice that I do go ahead and give you values for the sample mean, the sample standard deviation, and then the sample median. So I don't think in this problem you actually need to refer back to the raw data. In Part A, we're asked to derive the formula for the method of moments estimator for theta. So let me get to the right. There we go. So problem 3, we're given the PDF for theta. I'm sorry, that for X, it depends on the unknown parameter theta. And we know that this is non-zero for X between 0 and this unknown parameter value. So in the method of moments, we set, since there's only one unknown parameter, we set the first population moment, which is E of X. The second population moment would be E of X squared. But we set the first population moment equal to the first sample moment. I equal 1 to n of my xi. But the right-hand side here is just equal to my sample mean, okay, which, again, is a number for this particular observation. What I have to figure out for this part is actually what is E of X. That's going to be a theoretical value that actually depends on the unknown parameter theta. So E of X is, in order to determine the expected value, I integrate X times its PDF over X. Again, the PDF is only non-zero between 0 and theta. X 2x theta squared dx. So this is going to be integrating x squared. So what am I going to get? 2/3 x cubed over theta squared, evaluating at 0 and theta. So evaluating this with x equal to theta, I'm going to get theta cubed over theta squared. So that's just going to become 2/3. Theta is the expected value of x. And then so when I set these two equal and solve for theta, what I get is the method of moments estimator for theta. So I set my 2/3 theta equal to my sample mean, solve for theta, and I'm going to get 3/2 times the sample mean. So this is my method of moments estimator for this unknown parameter theta in this particular problem. Again, if there were two parameters, A and B, or theta 1 and theta 2, I would set the first sample moment, the first population moment equal to the first sample moment, like I did here, and then also set the second population moment equal to the second sample moment, so that I would have two equations and hopefully the two unknowns A and B, or theta 1 and theta 2, and then I would solve those two equations to come up with the corresponding method of moments estimators. Okay. Part B is just asking you what, for this set of data, what is the corresponding method of moments estimator for theta? And just plugging in, we're given x bar that was actually given to be 13.459. And then so carrying out that calculation, we get 20.19. Okay. From the description of the PDF, you know, none of our x values should be greater than theta, or correspondingly, theta should be greater than all of our x values. The largest x value here is, it looks like, is it the 17.55? So theta has to be greater than that particular value. The method of moments estimator method gives a value for that of 20.19. C, what is the expected value of the method of moments estimator? Okay, so here we're asking for E of theta hat. So that's actually the expected value of 3/2 x bar, using the properties of the expected value, and pull out the constant. Okay, and we looked at you know, the distribution of sample mean. I think that was in chapter at the end of chapter 5. But one of the properties there that we had is the expected value of the sample mean is equal to the population mean, which I actually have already caught. The population mean is E of x, so that's actually 2/3 theta. So this becomes theta. What this means, and it's not always the case that the expected value of the estimator is equal to theta. For this particular estimator, that is true. So this is what we would call an unbiased estimator. Okay. Expected value of theta hat is actually equal to theta. So that's a property we like to have. And D, you're given that the population median is equal to theta over the square root of 2. Use this formula to derive another estimator for theta based on the sample median. So you know, this is just kind of coming up with a common sense estimator. We would equate the population median. I don't even ask you to derive this. This is given to you. Set the population median equal to the sample median. So this is kind of similar to the method of moments, but it's another way to actually come up with an estimator. So let's see, what do we have there? Theta over the square root of 2. We set that equal to the sample median. So this will be yet another estimator. Solve this for theta. Theta then becomes the square root of 2 times our sample median. And so this is an estimator kind of based on this, you know, common sense relationship. This method doesn't really have a name like method of moments or maximum likelihood estimator or anything like that. And then I think also we're asked to actually plug in, find the value of this estimator for this particular sample. So plug in the median value, the sample median, to 14.506 here. Square root of 2 times 14.506. And that becomes 20.51, would be yet another estimator for theta for this particular problem. Again, it's pretty close to the method of moments estimator, and again, it is larger than any of the individual sample values. Not really sure which of these would be a better estimator. And one of the things we could look at is actually via computer simulation, look at histograms of these of these two estimators, and then we'd be looking at two things, which is um, um, unbiased. We know this one is unbiased, so this one is actually going to be biased, and then unless, I don't think that's true, square root of 2 times, yeah, they're both unbiased actually, because square root of 2 times the median is equal to the sample mean, but then also look to see which has the smaller variance. Okay, so I think that's it for this problem.